Welcome to this series on the MAX32660, a new low-power microcontroller from Maxim Integrated. In this first part, we'll explore the MAX32660 and see how it fits in with the other microcontrollers Maxim builds and set the stage for development activities. First, though, let's take the high-level view. The MAX32660 is the smallest and least expensive member of Maxim's family of ARM Cortex-M4-based microcontrollers. It also has the most modest power requirements, both when running in active mode and when sleeping. Let's take a look at the things that make the MAX32660 interesting. First is size. The MAX32660 is really tiny at just 1.6 millimeters on a side in the WLP package. Now, the thing about WLP is that some manufacturing processes don't really like the fine sub-millimeter bump pitch, and they prefer a larger package. Well, for those processes, we offer the same die in a 20-pin TQFN package. Other than size, the TQFN provides all 14 GPIO connections, while the WLP package provides just 10. Now, either way, this part is really fast. It's an ARM Cortex-M4 core running at 96 MHz with DSP extensions and a floating point unit, and a serial wire debugger. With the MAX32660, you give up nothing with respect to the core. Now, we've already mentioned price, but it's really important. This is the least expensive part in Maxim's portfolio, and its performance at that price point means the MAX32660 can replace discrete parts in many applications. And what you get for your dollar is pretty impressive. 256 kilobytes of flash memory, 96 kilobytes of RAM, and lots of peripherals, 3 timers, 2 UART channels, 2 I2C channels, 2 SPI channels, and a serial wire debugger. The peripherals communicate with the outside world over up to 14 GPIO pins, each with flexible assignment options. Now, even with its generous memory and peripheral complement, it's still conservative on power. In active mode, the power consumption is just 60 microwatts per megahertz. We can achieve this low power level because the device is manufactured on a 40-nanometer line. That's less than half the line size of the previous generation's 90 nanometers. Smaller feature size means lower gate capacitance, and that in turn means lower active power consumption when running at the same clock speed. But smaller geometry also frequently means higher leakage current, and that can wreck power consumption in sleep modes. But the MAX32660 shines here too. Sleep mode power, with all RAM retained, is just 1.8 microwatts. Small size means reduced pin count, but we don't let that limit the usefulness of this powerhouse. Each GPIO pin can be alternately configured to connect to a selection of up to 3 peripherals. Even the compact WLP package exposes every peripheral in the device. And finally, you can't overestimate the importance of the memory complement. With 256 kilobytes of flash and 96 kilobytes of RAM, you can run serious software on this part. And what's more, you can retain the entire RAM array while the part sleeps. That means when you restart, you don't need to reload the entire operating system. You can just restart where you left off. So that's the big picture. A tiny, inexpensive, but powerful microcontroller that just sips power. But I'd be misleading you if I told you that you don't make a few compromises with this part. Most obviously, with just 10 or 14 I/O pins, not every function can be used at the same time. But even with that limitation, you'll find there's a great deal of flexibility in assigning functions to peripheral pins. One of the features that really minimizes power consumption in some of our low-power microcontrollers is the Peripheral Management Unit, the PMU. It constitutes something of a second, much lower power core that can take over data movement operations in these parts. When the PMU is operating, the main core can be sleeping until needed. Now, the MAX32660 doesn't include a PMU, but it does include the standard ARM DMA controller, and that can operate when the main core is asleep. An optional feature for many of our microcontrollers is a trust protection unit. The TPU accelerates many security-related features and functions and makes complex, time-consuming algorithms easy and fast. Well, since the MAX32660 isn't really intended to be the main system microcontroller, it really doesn't make sense to put a lot of crypto functions there. One of the features we had to give up in the name of saving space is the ADC. See, good analog requires adequate silicon space, and on a part this small, there just wasn't room. Another feature omitted was SPI execute in place. But this time it wasn't silicon area, it was pins. There just aren't enough pins to spare to configure quad SPI. Finally, even though you have plenty of peripherals, you don't get quite as many as some of our other microcontrollers. In particular, there's no USB port. Again, this part isn't really intended to be a system-level micro, so a USB port is not a real requirement. But that's really everything. You're going to find that the MAX32660 is easy to use, easy to program, and a lot of micro for the size and the money. First, we're going to look at the pin interface. You'll get either 16 or 20 pins, depending on the package you choose. Whichever package you do choose, 6 of those pins are going to be dedicated to fixed functions. Let's have a look at those first. 3 of the 6 dedicated pins are there for power. There's a ground pin, of course, a pin for core voltage, and a separate pin for I/O voltage. Now, the use of 2 voltage pins is intentional, and here's why. In some applications, you need the absolute least number of components, and you can tolerate a little less efficiency. Now, for those applications, all you have to do is connect a supply to the VDD pin. An internal regulator generates the core voltage. You just put a cap on the V-core pin to filter the regulated voltage. Yes, the low dropout regulator inside the device dissipates a little power, but it's still the quickest way to get the device up and running. Now, if you want the very best efficiency, you turn off the internal voltage regulator and use one of Maxim's power management ICs to power the device. Maxim's PMICs use extremely efficient switching technology to generate both the I/O voltage and the core voltage from a single battery. By giving up just a tiny amount of board space, you can dramatically extend the battery life of your product. In fact, the power situation is just a little bit more complex than that. There are a lot more blocks than just I/O and core digital. Let's talk about that. The VDD connection drives a lot of blocks that don't need regulated power. For one thing, there's this extremely low power circuitry that measures the supply voltage to make sure it's in operating range. There's a logic block that has to be powered all the time, and this includes the real-time clock, a wake-up timer, and the power sequencing logic itself. And then there's the power to the charge pumps that are used when programming the flash. Now, of course, battery power has to go to the internal LDO, but there's also a micropower retention regulator that can't actually run the core, but it can provide enough power to keep the registers and the RAM intact when they're inactive. That second regulator is one reason the MAX32660 can achieve such low standby power even when everything is being maintained. The regulated power rail operates at about 1.1 volts when being driven by the main regulator and about 0.9 volts when being driven by the retention regulator. Now, of course, the main digital logic block takes power from this rail, but it also provides power to the flash array and the 96 MHz ring oscillator. Now let's talk about RAM. The system RAM is subdivided into 4 blocks, 2 of 32 kilobytes and 2 of 16 kilobytes. Well, why do we break it up this way? Because your application may not need to keep the entire RAM array when operating in the lowest power modes, and you may prefer to forego retaining the entire array in order to focus on longer battery life. You can select to retain 16, 32, 64, or all 96 kilobytes of the RAM. I know, it all looks pretty complicated, but the good news is that you don't need to worry about most of this right away. You can get your application running and then apply power reduction measures as you need. So that's power. Now what about clocks? Well, the main CPU clock is provided by an internal ring oscillator, but the real-time clock has to have better accuracy than that. That's why 2 of the remaining pins are there for a tuning fork crystal. This crystal guarantees the accuracy of the real-time clock. Now, if you're not using the real-time clock, then you can dispense with the crystal and just tie the input pin to ground. The last of the dedicated pins is the reset pin. If you're building a system with a PMIC, the PMIC will generally control this reset pin, holding it active until power is stable. But in a minimal system, you can just tie the reset pin high and internal logic will start the CPU at the right time. The rest of the pins, 10 on the WLP package and 14 on the TQFN package, are all assigned, by default, to GPIO. Well, except for bits 0 and 1, and we'll talk about why that's true in just a moment. It's GPIO port 0, bits 9 down to 0, or bits 13 down to 0. In addition to the GPIO function, each pin can be reassigned to as many as 3 alternate functions. It's by using these alternate functions that pins get assigned to the various peripheral devices. Now, a lot of microcontrollers have only a few options for GPIO. You select an input or an output, maybe it's high impedance or it's in open drain mode, and you get a few interrupt options. But in the MAX32660, really, you have a dizzying array of options. Okay, first, each pin is independently configurable. Now, if you configure a pin for an output, you can select the drive strength and the slew rate to match whatever the requirements of the device you're driving. If you disable the output, the pin is assumed to be an input pin, and you can configure a pull-up resistor, a pull-down resistor, or the level of input hysteresis. You can also choose to interrupt on a high level, on a low level, a rising edge, a falling edge, or on both edges. This may be the most flexible GPIO port out there. Yeah, flexible, yes, but wow, that sure looks complicated. Well, fear not, because controlling all of this isn't really that complex at all. Now, here's how it works. You're going to most frequently interact with just 3 registers: the input register, the output register, and the output enable register. Let's start with output functions. If you're just trying to toggle a bit, the default settings are probably good enough. But if you want to trim the output drive or the slew rate, here are the registers that manage those functions. Now, on the input side, you can choose the level of input hysteresis and pull-up and pull-down functions for each pin. Now, interrupts. Choose level or edge and positive or negative polarity for each pin. Then enable the interrupts and optionally allow it to wake the core. It's all right here. Now, the last thing is the alternate function select. These 2 registers work together to configure each pin for either GPIO or one of the 3 alternate functions. Now, speaking of alternate functions, you get your choice of 2 UARTs, 2 I2C ports, and 2 SPI ports, plus debug pins, an RTC reference clock, and a timer output. Notice first that every peripheral is available on both the WLP and the TQFN pin configurations. You just can't use everything at once. Here's what I mean. If you're using the WLP package and you want to use, let's say, SPI port 1, then you have to move the debug connections to bumps B3 and B4. But then if you also wanted to use I2C port 0, well, you're stuck. But even with the limitations, you still get access to just about everything. In a typical design cycle, first you'll figure out where to put the peripheral pins and make those assignments, and then you'll design your board around the chosen assignments. After that, in firmware, you make the function assignments. But how do you assign alternate functions to the pins? Well, the answer is this. It kind of depends. To start with, we should probably look at how to use the registers that define the alternate functions. Now, each of the 2 alternate function registers is really a collection of 14 bits, 1 bit for each GPIO pin. Taken together, each bit in each register comprise a 2-bit field that selects either GPIO functionality or one of the 3 alternate functions. Now, in this example, we're looking at GPIO bit 0. It can be configured for GPIO, for its alternate function 1, the serial wire debug, for alternate function 2, in this case the MISO pin for SPI port 1, or for alternate function 3, for this pin that's transmit data for UART port 1. Now notice that all the pins default to GPIO, except for bits 0 and 1, and they're assigned to the first alternate function, and that's serial wire debug. Why? Well, after all, you have to have some way to take control of the device right out of the box. But, you may not even need to think about pin configuration at all. There are a couple of reasons. First, there really aren't that many peripherals that offer their connections on multiple pins. Consider, the serial wire debugger by default appears on bits 0 and 1, and offers duplicates on bits 8 and 9. Choose the alternative, and you lose I2C port 0. But why would you choose the alternative in the first place? Well, think about the case where you really need two SPI ports. SPI port 1 appears by default on bits 13 down to 10, and that's fine if you're using the TQFN package, but if you're using the more compact WLP, well, you don't get bits 13 down to 10. But if you really need that second SPI port, just move it to bits 3 down to 0. Now, of course, that means the SWD default pins in I2C port 1 aren't available, but in this life, sometimes you just have to pick and choose. We find UART1 in the same pickle. If you use the TQFN package, you can configure UART1 on bits 13 down to 0, but on the WLP, you don't have those bits. You can move that UART to bits 0 and 1, but that forces you to move the debugger and precludes the use of the second SPI port. Alternately, you can move the UART down to bits 7 down to 6. But that'll conflict with SPI port 0 and the flow control bits for UART channel 0. As you see, you really do have access to all the peripherals, but you may have to choose which ones are most important to you. There are two more pins you can configure for special functions. There's a calibration output for the 32 kHz real-time clock oscillator, and an output bit from timer channel 0. Select either of these, and you'll give up the second I2C port and the second SPI port. Now, the good news is that even though you do need to think about how you want to configure the part, you really don't need to think about the individual bits. That's because the board support package handles most of the initialization tasks. A set of routines provided in the board support package for the MAX32660 provide a method for automatically configuring pins. Here are the prototypes for the I2C, SPI, and UART initializers. Now notice, each one accepts a pointer to a sysconfig structure. One of the elements in that structure is a sysmap. Now, the I2C port can't move, so the pointer is void. But each of the SPI and UART initializers accepts a sysmap type, and that tells the initializer how to map the pins. Now, the initializers don't handle conflicts, so you still have to be careful, but it sure helps. As we talked about when we looked at the pin functions, if simplicity is your rule, then power is really easy. Just connect some power to VDD. Anything from about 1.6 to about 3.6 volts will do. And the device will start running. The internal LDO regulates the input voltage to the approximately 1 volt needed by the logic. And when power is applied, the device will begin running from the reset vector, and you take control with a serial wire debug port to load code on the device. And if you do nothing else, the device will continue to run that way. Maximum clock, maximum power. This is called active mode. And it's still pretty low power for this class of processor, but at 60 microwatts per megahertz, at full speed it's dissipating something north of 5.5 milliwatts. That's not the best we can do for a low-power microcontroller. Now, one way to manage power is to stop the core when it's not being actively used. You can leave the power on, but stop the clocks to the main core. To do this, you'll use the ARM instructions wait for event and wait for interrupt. These instructions stop the main core, but leave power applied to the core and its peripherals. So the core retains its state and the peripherals continue to operate. Now, since dynamic power is the main factor in overall power consumption, this dramatically reduces power while the core is waiting for an external event. This is called sleep mode, and it's the first of the MAX32660 low-power modes. In sleep mode, Any of the peripherals, including the DMA controller, can wake the core, and it will continue execution with the instruction immediately after the one that put the core to sleep. It's a quick, easy way to manage your power budget. But what if all you want to do is just, sleep? Sure, you need to wake periodically, but you don't need to have any peripherals active. Well, that's the function of deep sleep. In deep sleep mode, the master oscillator is turned off, so the device is drawing only leakage current. The only things that will wake you in deep sleep is the RTC alarm and the GPIO pins. But notice, even in deep sleep mode, the core state, the RAM contents, and the state of the peripherals is maintained. Now, they're not getting clocked, but you can still get back to a working state in a hurry. But maybe you need the very lowest power consumption, and if it takes a few microseconds to get running, well, that's okay. Well, that's why we included backup mode. In this mode, only the RTC remains active, and power is removed from all peripherals and the CPU core. Additionally, you can select how much of the 96 kilobytes of RAM to backup: 16, 32, 64, or all 96 kilobytes. The unselected RAM blocks are completely turned off, and they don't drain the battery. Now, of course, you can also modulate the clock speed if you don't need to run at the full 96 megahertz. Once again, dynamic power dominates power consumption, so this is another good way to manage power. There are 3 clock sources: a 96 megahertz high-speed clock, a 32 kilohertz RTC clock, and a very low-power 8 kilohertz nanopower ring oscillator. Now, in some of our other devices, there is some interaction between clocks, but in the MAX32660, the relationships are much simpler. Let's take a look. First, I want to draw in the 3 oscillators. Notice first that both the nanoring and the RTC oscillator are in the always-on power domain, although there is a bit that turns off the RTC oscillator if it's not being used. The 8 kHz nanopower oscillator always runs. The 96 MHz oscillator can be switched on and off. The RTC clock is the only oscillator that uses a crystal. Both the nanoring and the high-speed oscillator are free-running, and there is no mechanism to control the frequency of the high-speed oscillator with the RTC oscillator. So if you need precise timing, you're going to need to use the alarm or the periodic interrupts from the RTC. The RTC takes the 32 kHz clock from the RTC clock, along with a 4 kHz clock derived from the RTC clock. The 4 kHz clock is the one that actually drives the RTC counters. The 32 kHz clock is used to trim those counters. The 8 kHz nanoring output drives the power sequencer. Now, the cool thing is that any of these clock sources can actually drive the CPU and peripheral chain, and once that choice is made, you can scale the clock by a factor of 1 to 128. So here's the deal. You can run the CPU at any frequency from a high of 96 MHz down to a low of 8 kHz divided by 128, or 62.5 Hz. There are 2 fields you need to think about when you configure the clock, and both are in the GCR block, in the clock control register. The first is a 3-bit field that selects which oscillator to use. Now notice, only 3 of the 8 possible codes are allowed. If you select a reserved code, it might crash the microcontroller, so be careful. The other field is the prescaler field. It's a 3-bit field that allows you to select the prescaler value from 1 to 128. With just those 2 fields, you can effectively manage the clocks, but there are more fields if you want even finer control. In the GCR clock control register, you'll find enable, disable, and status bits for the oscillators, as well as the scaling and selection fields we just talked about. And also in the GCR, you have individual clock enable bits for each peripheral. Turn off the clock to a peripheral, and you've eliminated virtually all of its power consumption. One of the things to consider is that our low-power microcontrollers are designed to operate from a battery, and frequently a rechargeable battery. If your application is battery operated, true power on reset is a rare event. But reset is something you have to consider, and the MAX32660 gives you 4 reset options: power on, system, soft, and peripheral reset. All the reset types really do reset the core. That is, after a reset, the core begins executing code at the reset vector. Reset also resets the clock selection back to the high-speed clock, which gets automatically enabled. All the peripherals are reset, and any low-power modes are canceled, and the device is placed in active mode. So that's what all the reset modes have in common, but each reset type has unique characteristics. Let's start with the least intrusive reset, peripheral reset. Now, in this type of reset, the peripheral devices are reset. Any peripheral currently in a transaction is immediately reset and the transaction is abandoned. The CPU retains its state, but it begins executing at the reset vector. Now notice, the general configuration register block, the GPIO pins, the watchdog timer, and the contents of RAM all are preserved. That means that the CPU doesn't have to reconfigure everything. It can reestablish low power modes and get right back to work. Soft reset is similar. The CPU and the GCR are preserved, as is RAM. But soft reset forces all pins back to their default state, and that means GPIO configured as input, except for bits 0 and 1 and their serial wire debug. You'll need to reconfigure any alternate functions to recover after a soft reset. A system reset is as close to a power-on reset as firmware can command. A system reset resets everything except the power sequencer and the contents of RAM. It's pretty much a do-over. Firmware has to configure everything. And then finally, there's power on reset. And the only way to get to power on reset is to physically remove power. And that destroys the contents of RAM. It also resets the power sequencer, so you're truly starting from zero. If your software is properly engineered, you should never actually need to do a power on reset. Another reset should get you back up and running. Actually, you may not need to reset the core at all. Every peripheral block has its own reset bit. Here's a map of all the peripheral reset bits. And notice, the bits to trigger a soft, peripheral, and system reset, well, they're right here too. The MAX32660 isn't designed to be a system microcontroller. You're not going to find a security block or a USB port, and you're not going to find advanced communication peripherals like Bluetooth, but nevertheless, for such a tiny part, the peripheral complement is pretty complete. You get 2 UARTs, 2 SPI ports, 2 I2C ports, 3 timers, and the debug port. Let's start with that last. The debug port is ARM's serial wire debugger. It's really very well supported, and it includes both debugger and loader functions. On most boards, it will be paired with one of the UART channels to create the interfaces most frequently needed for system bring-up: loader, debugger, and a UART console interface. Now, most frequently, your application board will contain a 10-pin DAP-Link connector that will be cabled to a debug adapter. 2 of the 10 pins will carry the signals from the serial wire debug port. The other pins will connect the console interface. The debug adapter will in turn connect to your development computer, most frequently through a USB connection. The serial wire debugger does all the things traditional JTAG does, but with fewer pins. Now, by default, the serial wire debug port is enabled on GPIO bits 0 and 1. Those bits are assigned to bumps C1 and C2 on the WLP package, and to pins 1 and 2 on the TQFN. On the WLP, this position precludes the use of the second UART and the second SPI port. If you need either of these ports, you can move the debug port to IO port bits 8 and 9. Now let's turn to the UART channels. There are 2 UARTs available on the MAX32660, each with hardware handshake. Due to the reduced pin count, the WLP version doesn't expose the handshake signals on the second UART. Each UART has its own independent baud rate generator based on an overflow accumulator rather than a clock divider. Now, in this arrangement, the clock frequency is closer to the ideal baud rate as the baud rate increases. That's ideal for modern serial ports that typically run at 115,200 baud or faster. You'll typically configure the pins to operate at conventional 3.3 volt logic levels, and if you need real RS-232 signals, you'll use a level shifter. The UARTs are on bits 7 down to 4 and on bits 13 down to 10 as alternate function 2. You can also put UART 1 on bits 1 down to 0 and bits 7 down to 6. Now let's take a look at the I2C ports. Both I2C and SPI are most frequently used to provide communications between chips in a system. The big difference is that I2C requires only 2 wires and carries the device address as part of the message, while SPI depends on 3 wires plus an additional wire for every device it needs to address on the bus. I2C ports are always a little problematic because there are low-level protocol elements like start, stop, and repeated start that have different meanings in different contexts. The good news is that these details are handled by the hardware and the BSP drivers. For most applications, simple calls to the BSP can be used to initialize and communicate using the I2C ports. The I2C ports are the first alternate function on port bits 2 and 3 and port bits 8 and 9. Next up are the SPI ports. There are 2 SPI ports on the MAX32660, but they're not identical. Even though they share the same basic features of any SPI connection, the register configuration and operational modes are different. Now, the primary difference is that SPI port 0 has a deeper FIFO at 32 entries for transmit and receive, rather than the 16 entries for SPI port 1. SPI port 0 also allows finer control of the relationship between clock and data. But SPI port 1 can be operated as an I2S receiver in audio codec applications. Now, the user's guide has a lot more information about the specific differences between these devices. SPI port 0 is the first alternate function on port bits 7 down through 4, and SPI port 1 is the first alternate function for port bits 13 down through 10. Now, since bits 13 down through 10 aren't available in the WLP package, you can also expose SPI port 1 on I/O bits 3 down to 0, alternate function 2. There are a couple more pins to talk about. Timer channel 0 has an output pin as an alternate function on I/O bit 3. You can program timer channel 0 to provide a series of periodic pulses or to serve as a PWM output. Now, if you demand the very highest real-time clock accuracy, you can program I/O bit 2 to output the 32 kHz clock directly from the RTC. You can then trim the oscillator using the trim mechanisms of the real-time clock. You should refer to the user's guide for more information about this. Here's the bottom line. The MAX32660 may not be your first choice for a system-level microcontroller, but for small embedded applications and coprocessors, you sure get a lot for your money. An ARM Cortex M4 with floating point unit and DSP extensions in a tiny package, low power modes that just sip power, and a really nice collection of peripherals, all for a very affordable price. That's the MAX32660. Now next time, we'll look at the MAX32660 evaluation kit and some of the demonstration programs that come with the kit and the development environment. See you then!